My name is Rishabh and I am from CSE AIML branch and I'm gonna this reports present a complex engineering solution to a classic jump game problem using object-oriented programming in Java. The documentation covers problem definition, mathematical modeling, software design UML class description, algorithm choices, Java implementation, test plan and results, performance analysis, possible extension and conclusion. The focus is on engineering thinking, modular design, maintainability and testability. Table of content, introduction and problem statement, mathematical model and requirements, design goals and non-functional requirements, object-oriented design, key classes and responsibility, UML like overview, algorithms and engineering trade-off like greedy, dynamic programming, VFS or graph modeling, Java implementation, package structure, important classes with explanation and full code listing with core testing and validation, test cases and results, complexity analysis, extension and future work, and at last conclusion. Introduction and problem statement. The jump game is commonly studied algorithmic puzzle. Given an array nums of non-negative integers, each element represents the maximum jump length at that position. Determine if you can reach the last index starting from the first index. A more complex variant asks for minimum number of jumps to reach the last index or for all ways to reach the end. This report treats the problem as an engineering task and builds a reusable, extensible, object-oriented Java solution that supports multiple algorithm instrumentation for performance measurement and unit-style tests. Mathematical model and requirements. Input. We have to store the array nums from 0 to n minus 1 of non-negative integer. Problem considered. Feasibility. Can we reach index n minus 1 from index 0? For that we have to declare a boolean minimum jumps. What is the minimum number of jumps to reach n minus 1? Int or minus 1 if unreachable. Parts. Optional complexity. Enumerate valid sequence of indices that reaches the end. The constraint n can be a large number from 10 power 5 or more in some tests. Values in nums can be 0. Solution must handle worst case inputs efficiently. Design goals and non-functional requirements. Modularity. Separate problem interface, algorithms and utility. Extensibility. Allow plugging new algorithms without changing client code. Testability. Easy to supply test inputs and compare outputs. Observability. Provide timing and step count for algorithm comparison. Performance. Use algorithm the scale to large n. Object-oriented design. Jump game interface defines API method can reach and mini jumps. Abstract jump game method. It's an abstract method, common utilities, validation and instrumentation. Greedy jump game. It is a concrete method. Greedy algorithm implementation for method can reach and min jumps. DP jump game. Dynamic programming based on implementation for mini jumps method. BFS solver. BFS graph style solution for shortest path min jumps mostly for clarity and smaller inputs. Jump game factory produces instance based on enum and strategies. Benchmark measures runtime, mirror usage, and steps counts. Test suite contains test cases and runs algorithm for comparison. Results data class holds results like boolean reachable, min jumps, time ms, and steps. UML like overview Jump game, abstract jump game, greedy jump game, DP jump game, and BFS solver. Jump game factory, benchmark, test suite, and results. Now further, we are going to discuss about the algorithms and engineering trade-off used in this code jump game. Greedy for can reach and min jumps. Idea maintain the farthest reachable index while scanning left to right. Complexity of time. O and time or O 1 extra space. Pros fast minimum memory. Cons implementation details needed to also produce mini jumps, slightly more bookkeeping but still in a complexity space of ON. Dynamic programming for min jumps. Java implementation. Below is a compact, well-documented Java implementation illustration for the OOP approach. The brevity focuses on core classes, package structures, com example jump game, jumpgame.java, abstract jumpgame.java, greedy jumpgame.java, dp jumpgame.java, bfs solver.java, jumpgamefactory.java, benchmark.java, testsuite.java, and result.java. So it's time to understand the code and implement it through Java. So here we declare the contract for any implementation. Both methods return a result object, so each implementation can include runtime instrumentation. Keeps API consistent, so called can switch algorithm strategies easily. Reachable. Whether the last index is reachable, min jumps, minimum jumps, or -1 if unreachable for not computed. Time ms. Elapsed time in milliseconds for that method called computed using system.nanotime method, then converting to ms. Steps. An instrumentation counter increment by step in implementation representing algorithm step inspected indices useful for micro benchmarks and comparing internal work independent of wall time. After that, we have to override the method and return in a string format having reachable min jumps, time ms, and steps. Abstract class and greedy implementation provides a step counter to measure number of logical operators whenever they perform a basic unit of work, example inspect of index. Reset step method clears counters at the start of each run. Validate method performs null checks, quick defense programming. Abstract class reduces duplicate code and enforces consistent instrumentation. Greedy jump game. We have to override the method and initialize n is equal to nums.length and farthest length is equal to 0. And we have to implement a loop starting from 0 to n minus 1. If num's length is n, initialize the farthest is equal to 0. Loop I from 0 to n minus 1. Steps to count inspection of I. If I is greater than farthest, break because we cannot reach index I. Update the farthest is equal to max farthest, comma I plus num of array I. If the farthest is greater or equal to n minus 1, we can reach the last index and return result, which is through 0, comma time ms, comma steps. If loops finishes without reaching n minus 1, return the results false minus 1, time ms and steps. DP and BFS brief snips. We are extending the abstract Java game. We are initializing G is equal to new greedy jump game and returning G dot can reach nums. We are overriding the method in this slide. So basically we have to define n, which is nums.length, and an array of dp. And at a final we have to define an int variable which is inf integer max value. and after that we have to run a for loop. After initializing the values, we have to run for loop from 0 to n minus 1 steps method from j from I plus 1 to min n minus 1 I plus num I. If dpi is finite, set dp of array j is equal to min dp of array j, comma dp of array I plus 1. We have to return a answer has minus 1 time mf and steps. Factory and benchmark. Factory patent to easily swap algorithm implementation in client mode. Useful for running comparison or test without changing calling code. Benchmark. Benchmark is recommended to measure time mf, wall clock from results, step, instrumentation from result, optional memory usage or peak allocation not implemented. Testing and validation. Test cases. An empty array behavior reject has invalid. Of an array 0, single element reachable, min jumps is equal to 0. For an array 23114, a classic reachable min jumps is equal to 2. For an array 32104, blocked unreachable min jumps is equal to minus 1. A random large array is equal to stress test for performance vary lengths, example like 1k, 10k and 100k. Worst case arrays like array 1111 size 100k check linear versus quadratic scaling. For example, touchscreen input for array 23114 can reach through greedy times small. Min jumps 2, greedy returns 2. Input for 32104, which is an array, can reach is false. Min jumps is equal to minus 1. Record timing and step counter to compare algorithms. Multiplicity analysis. Greedy. On time O1 extra space best for production dp O n square time worst case or on space useful for small n or when enumerating parts. BFS OE where E can be On square worst case or On space for Q. Memory footprint is small for greedy. DP stores an On array. BFS may require an additional bookkeeping to store visited nodes and parents. Extension and future work. Enumerate all the shortest path. Maintain parent list during BFS. Weighted jumps. If each index has cost, use Dijkstra-like approach to minimize cost rather than jumps. Concurrent solver. Parallelize parts of DP or run multiple strategies concurrently and pick best trade-off. Visualization. GUI or web visualizers showing jumps of an array. Persistent logging and telemetry for performance across input runs. Conclusion. This report presented an engineering approach to a jump game focusing on object-oriented Java design that separates concerns, allows multiple algorithmic strategies, supports extreme extensibility for large-scale inputs. The greedy approach is a recommendation due to the linear learn time and minimum memory usage. The DP and BFS approaches are valuable teaching tools and useful for path enumeration or small units. Thank you.